Welcome to this tutorial in multiple comparisons in fMRI using BrainVoyager. This tutorial is designed to familiarize the user with the correctional aspects of fMRI data analysis using the BrainVoyager version 20.6.1.3265 software. More specifically, this tutorial aims to impress upon its users the importance of implementing correction methods in neuroimaging data analysis, as well as to discuss the key benefits and limitations of three well-known correction methods: Bonferroni, false discovery rate, and cluster correction. This video is supplemented by a Word document which will provide the theoretical background for the information provided in this video. We recommend referring to the Word document for the full benefit of this tutorial. The actual pace of this video does not reflect the time that it will take to fully grasp the information in the tutorial. Please speed up, slow down, skip, and pause the video where you feel appropriate. The information from this tutorial can be applied to any neuroimaging data requiring corrections, but for the specific purpose of this tutorial, we will be analyzing a dataset of 12 participants where the activation in the face-specific areas of the brain was measured in response to photos of faces and hands where the direction of gaze and pointing was experimentally manipulated. Learning objectives. After completing this tutorial, you should be able to understand the pros and cons of the three different multiple comparison methods: Bonferroni, false discovery rate, and cluster correction. You should also have a solid understanding of how to carry out the corrections using BrainVoyager and understand when it is appropriate to use each type. Finally, you should be able to understand the strategies that can be used to avoid experimenter bias in data analysis for techniques such as cluster correction. If you feel like a concept is unclear or require more information about a correction, please refer to the Word document and the references provided. Prior to beginning the tutorial, please ensure that you have the following files loaded, as they will be required for the different sections of this tutorial. We will begin by going over a few key statistical terms that will allow you to better understand the different correction approaches as well as what they hope to achieve. Type 1 errors refers to the rate of false positives. In other words, things that are shown to be true by our analysis but are actually incorrect, as you can see indicated on the table. Example of type 1 errors include voxels that are activated by chance. Type 2 errors refers to the rate of false negatives. In other words, things that are shown to be untrue by our analysis but are actually true. Examples of type 2 errors include voxels which should be activated but are not. Corrections can be used as a solution to the multiple testing problem. The multiple testing problem is present when our analysis requires a large number of statistical tests. The more tests we run, the more conservative our threshold criteria must be. This is a particularly pertinent issue in neuroimaging. In functional neuroimaging, one might find that voxels may be activated outside the areas of the brain. We do not want to include these voxels in our analyses. A simple sanity check of the data can be performed for casual data exploration. This will be called the poor man's Bonferroni. By manually adjusting threshold values, we can remove activation outside of the brain. This method, however, will apply the threshold uniformly across the entire image. As a result, voxels within the brain will be reduced alongside those outside the brain. It is up to the discretion of the researcher to determine what threshold is ideal in each case. Now, let's take a look at how we can carry out the poor man's Bonferroni in BrainVoyager. Go to the File window, select Open. Select the average n is equal to 12 VMR. Select Open. Go to the Analysis window. Select Overlay General Linear Model. Load the GLMs of interest. We will be loading the group localizer. Select Open. Select the contrast of interest. We'll be looking at faces +1, scrambled -1, which is indicated at the bottom. Select OK. So as you can see, these are all the voxels that are activated inside and outside of the brain. You can see there are voxels that are activated outside of the brain. In BrainVoyager, there are two buttons that you can click to either decrease or increase the threshold. So if I increase the threshold, you can see that some of the voxels outside of the brain disappear. Similarly, if I decrease the threshold, then you can see the voxels reappear. Please feel free to play around with this to try and figure out what would work best for you in terms of reducing the amount of activated voxels outside of the brain. Please note that this method is most appropriate only for casual data exploration. A more formal approach to removing activation outside of the brain is by applying a mask. The mask will dictate which voxels will be considered in your analyses. Think of it as a process that creates a border around the area of interest and negates any voxels outside this area. Now we're going to take a look at the effect of a mask on BrainVoyager. Don't worry about following the steps. Rather, focus on understanding the role of a mask and how, in our case, it removes voxels outside of the brain. As you can see here, this is the average n is equal to 12 VMR of the faces minus scrambled condition. So we're going to alternate between the mask and the VMR. So see, when we apply a mask, what it does is that it creates an outline around the brain and effectively takes into account the voxels that are activated outside of the brain and removes them. So we're going to switch back to the average is equal to 12 VMR. You can see the voxels that are activated outside of the brain. When we apply the mask, those voxels are no longer considered.
The first correction method we are going to be talking about is the Bonferroni method. The Bonferroni method takes the probability of false positives and divides that by the number of tests run. A drawback of Bonferroni is that it is at times too conservative. It assumes that each voxel is independent of the others, which is not the case. In the case of fMRI data, adjacent voxels are more likely to be significant than non-adjacent voxels. Please take a moment to consider the following questions. Question 1. When would you use a more conservative correction method, such as Bonferroni? Question 2. How can we modify the threshold values on BrainVoyager? What impact do these modifications have on the results? Let's start with a step-by-step tutorial on how to conduct a Bonferroni correction on BrainVoyager. Select the File window. Select Open. Choose the file of your choice. We will be using the average VMR data. Select Open. Now go to the Analysis window. Select General Linear Model Multi-Study Multi-Subject. Now load the MDM file. Select the data of your choice. We will be using the group localizer data. Select Open. Now go to the Options tab. Here we will be adding the mask. Press Browse. Add the mask file. We will be using the 2mm mask. Press OK. Now press Go. Wait for the GLM to run. Go to the Analysis tab. Now overlay General Linear Model. Select the conditions of your choice. We will be looking at faces minus scrambled. You will have to deselect the conditions that you are not interested in. It should look like faces plus 1 scrambled minus 1. Select OK. Go to the Analysis tab. Select Overlay Volume Maps. Go to the Statistics window. Use statistical value rather than the FDR. Now go to Map Options and use the Bonferroni p-value. Select Apply, and now close. As you can see, the Bonferroni is a highly conservative test. Very little data has survived. Here we will highlight the only small portions of activation that have survived the Bonferroni test. Go to File, Open, and select the average data again. Select Open. Now go to Window and select Tile so that we can see two things side by side. We will compare the faces minus scrambled to another condition. Select the Analysis tab and go to the Multi-Study Multi-Subject tab again. Do the same thing you did before by loading the MDM, load the group localizer file. Options, and load the mask. Let the GLM apply. For this condition, we are going to load the faces minus body and compare it to the original faces minus scrambled. Go to the analysis window. Overlay General Linear Model. Select faces minus body. It should look like faces plus 1 and body minus 1. Now select OK. Here, we can see the data that has survived this Bonferroni test, and you can make comparisons between this condition and the faces minus scramble condition. If you link the VMRs, you will be able to move your mouse across and see what areas are activated in both of the brains. Now, we will be comparing the regions that survived the Bonferroni correction to a set of face-specific regions defined by the NeuroSynth database. Select the File window. Now press Open. Select the data you're interested in. We will be using the group average VMR. Select Open. Now select the Analysis window. Select General Linear Model Multi-Study Multi-Subjects. Load the MDM. We will be using the group localizer data. Press Open. Now select Options. Add your mask. We will be using the 2mm mask. Press OK. Now press Go. Let your GLM load. Return to the Analysis tab. Now overlay General Linear Model. Select the conditions you're interested in. We will be looking at just faces. It should look like faces plus 1. This is all the activation of just the faces. Go to the Analysis window and press Overlay Volume Maps. Now go to the Statistics tab. Make sure to be using the statistics value rather than the FDR. Go to Map Options and select the Bonferroni p-value. Press Apply. Now close. Here you can see that the Bonferroni has eliminated most of our activity. Now let's compare it to the NeuroSynth database. Select Open and open the average data once more. Go to Window and select Tile so we can see the two side by side. Link the VMRs. Now go to the Analysis tab and select Region of Interest Analysis. Press Load and load the NeuroSynth database. Select Open. Now we can look at the activity in the face-specific regions. There is the left and right fusiform area. We can show them on the NeuroSynth database. The left and right amygdala, the STS, and the right and left OFAs. Let's show them all. Press Close. Now we can compare, and we might notice that the Bonferroni correction has removed most of our face-specific activity. We can conclude from this that the Bonferroni test was too conservative for our purposes. If we compare an individual subject to an average group dataset, we will notice more voxel activation in the individual. Averaging participants together removes individual idiosyncrasies, resulting in an average pattern of activation. This will reduce the overall activation. Depending on your specific purposes, these idiosyncrasies may be of value to you. Neuroimaging studies have shown that analyses at the individual level may capture significant inter-individual relationships that have promising applications. In turn, studies do show that aspects of the bold signal, such as functional connectivity, can be quite reliable across individuals. Given the merit to both individual and group-level analyses, the onus is on the researcher to determine which approach works best with their specific data. Now, let's take a look at the participant 2 versus the group data after the Bonferroni correction. We are comparing an individual to a group dataset. We can see that the participant 2 has more activation in all areas when compared to the group dataset. For our purposes, we can conclude that the Bonferroni may work better for individual data than for the group average. Here, we will give you a closer look at the individual face areas and compare them to what survived the Bonferroni test. First, we will look at the fusiform face area, also known as the FFA. On the left, we have the NeuroSynth database, which shows what face areas are where, and on the right, we have what survived the Bonferroni test. As you can see, nothing survived. Now, we will look at the amygdala. On the left, we have the NeuroSynth database, and on the right, we have what survived the Bonferroni test. As you can see, nothing survived. Now, we will look at the superior temporal sulcus. On the left, we have the NeuroSynth database. On the right, we have what survived the Bonferroni correction. As you can see, nothing survived. Now, we will look at the occipital face area, also known as the OFA. On the left, we have the NeuroSynth database, and on the right, we have what survived the Bonferroni correction. As you can see, nothing survived.
Now we will be moving on to the second method of interest, the false discovery rate. The false discovery rate controls the proportion of rejected hypotheses that are falsely rejected, controlling for type 2 errors. The standard p-value represents the proportion of all voxels that are significant by chance. FDR uses a q-value, which represents the proportion of activated voxels or clusters that are false positives or significant by chance. It has been argued that FDR is not suitable for analysis at the voxel level, but rather it should be used at the cluster level. This is because the FDR lacks spatial specificity. It cannot deduce the significance of a single voxel. Generally, it is okay to use the FDR for both voxel and cluster level analyses, but researchers should take into account the limitations of FDR spatial sensitivity when doing voxel-wise analysis. A drawback of FDR is that it too can be very conservative in certain scenarios, for example when there is very little activation to begin with. In turn, it can be overly liberal when there is a lot of activation. We will now move on to a step-by-step tutorial on how to conduct a false discovery rate correction on BrainVoyager. Start off by going to the File window. Select Open. Select your file of interest. We will be using the P02 anatomical VMR. Click Open. Go to the Analysis window. Select General Linear Model, Multi-Study, Multi-Subject. Load the MDMs of interest. We will be using the P02 Localizer FFX MDM file. Click Open. Go to the Options tab. Select the mask file by clicking Browse. Select the brain mask N is equal to 12 2mm mask. Select Open. Click OK. And hit Go. Wait for the GLM to load. This is the activation for all the different regions. Go to the Analysis window, select Overlay General Linear Model, and select the specific comparison of faces minus scrambled. So deselect body, deselect hand, and make sure scrambled is minus. So you see faces +1, scrambled -1. Select OK. Now you can see the regions that are left that are activated. Go to Analysis, select Overlay Volume Maps. Go to the Statistics tab. As you can see, FDR is the default option on BrainVoyager, so everything that's active is using the false discovery rate. And once again, you can see the different regions that were activated. Go to File, Open, P03 Anatomical. So we're going to be comparing P02 to P03. Once again, you can go to Window, select the Tile option, and view P02 and P03 side by side. So for P03 and P02, for P03 we're going to hit Analysis, go to the General Linear Model, Multi-Study, Multi-Subject, and follow the same steps by loading the MDM, which is specific to participant number 3, P03, Localizer FFX, hit Open, go to the options, and select the mask file. So this is a 2mm mask. I'm going to click Open, OK. I'm going to select Go, and wait for the GLM to load. So once again, we're going to specify our contrast, so Analysis, Overlay General Linear Model, and we're going to select faces minus scrambled, and deselect bodies and hands. So as you can see at the bottom, once again, we have faces +1, scrambled -1. Click OK, and now we can see the comparison between the two different groups. So we go to the Analysis window, and we select Overlay Volume Maps, and go to the Statistics tab. Once again, you can see that FDR is the default option. Now we can compare the differences between the two by linking the VMRs. So when we move our cursor around, we can see the brain regions that are activated for P03 and for P02. So some regions are activated for P03 and not P02. This just goes to show you that there are differences even at the individual level. So you can play around with this and move your cursor around to see different regions that are activated for each of the participants. So we're going to show you a few regions. So in this case, there's some areas that are activated as part of P03 but are not part of the brain in P02, and different regions at the back of the brain. Feel free to play around with this. Here is an image of the group versus individual comparison for the false discovery rate. Please refer to this image when answering the question on your handout. Please take a moment to pause the video and answer the question on the tutorial handout. Question 3. How would corrections compare for individual subjects versus group averages? In our case, the false discovery rate is a more liberal approach than Bonferroni. When compared to the Neurosynth database, we can observe that most activation in the face-specific areas of the brain survives. Here we will give a closer look at individual face areas and compare them to what survived the FTR correction. We will begin by looking at the fusiform face area, also known as the FFA. So on the left we have the Neurosynth database, which indicates the location of the left and the right FFA. On the right, we have the corrected group analysis for the false discovery rate. As you can see, indicated by the red box, the FFA survives the false discovery rate correction. Next, we'll be looking at the amygdala. So on the left, we have the Neurosynth database, and it indicates where the left and the right amygdala are located in the brain. On the right, we have the group analysis, which has been corrected using the false discovery rate. As you can see indicated in the red boxes, the left and the right amygdala do survive the correction. Now we'll be looking at the superior temporal sulcus. Once again, on the left you can see the Neurosynth database, and the region indicated by the blue dot is the right superior temporal sulcus. On the right we have the group analysis corrected using false discovery rate, and as you can see there are certain areas which look like they're close to the superior temporal sulcus, but we see no direct activation of that region specifically. Finally, we'll be looking at the occipital face area. So once again, on the left you have the nearest database, and it indicates the left and the right occipital face area. On the right we have the group analysis corrected using the false discovery rate, and as you can see indicated by the red boxes, there is activation in the left and the right OFA.
Now, let us move on to the third correction we will be demonstrating in this tutorial, the cluster correction. The cluster correction method calculates random iteration patterns or Monte Carlo simulations of voxel activity based on the smoothness of the data. Each iteration gives us a possible cluster size at random. Based on the cluster correction, one can determine the likelihood that a given cluster of voxels would be activated by chance. When using the cluster method, we must set a minimum cluster size, or K value, to be large enough that a cluster of that size is unlikely to occur by chance. This method is highly flexible in that it allows the experimenter to manipulate several levels of criteria. This can be seen as a bug and a feature. To elaborate, while it may raise the risk of selectively manipulating data to fit a given hypothesis, it can also allow us to use judgments based on previous literature to choose the ideal criteria for our purposes. One drawback of the cluster correction method is that small regions are wrongly negated more than large regions. A danger of methods with a high degree of flexibility, like cluster correction, is that it increases subjectivity and the likelihood of p-hacking. P-hacking refers to when we alter our threshold values to produce a favorable result. In other words, we force our data to fit our hypotheses.
We will now move on to a step-by-step tutorial on how to conduct a cluster correction on BrainVoyager.
Go to the File window. Select Open. Open the file of your choice. We will be looking at the group VMR data. Return to the Analysis tab. Select Overlay General Linear Model and load the GLM. Select the Group Localizer data. Select the conditions that you are interested in. We will be looking at faces minus scrambled. It should look like faces +1 and scrambled -1. Select OK. Return to the Analysis window. Go to Overlay Volume Maps. Go to the Statistics tab. Here, make sure you're using a statistical value and not the FTR. Now, alter the p-value. The p-value will impact the cluster size. A greater p-value will produce a greater random arrangements of clusters. Go to Plugins and select Cluster Level Statistical Threshold Estimator. Select 1 for this since you are looking at only one image. Press OK. Now select No since this is already the value you have chosen. Select OK for the standard value. And here you would like to apply a mask, so select Yes. Choose the 2mm mask. No, you do not. Here, enter the number of iterations you would like. The more iterations, the more reliable your result will be. Let the iterations calculate themselves. Here your result is 47. This is the cluster size at an alpha level of 0.05. If you scroll up and find this alpha level, so 0.05, you will see it corresponds to the same 47 cluster size. Return once more to the Analysis tab. Go to the Overlay Volume Maps and go to Statistics. Here, you will see the cluster threshold. It should say 47. Now, please take a moment to pause the video and answer the questions on the tutorial sheet. Question 4. Why is the cluster correction result subject to change each time you run it? Question 5. How could we compare the faces minus scrambled condition to the faces minus body condition when both of these will yield different cluster values? Try performing the cluster correction yourself for both of these conditions to compare them. You will find that the faces minus scrambled condition will have a cluster threshold value of around 47, and the faces minus body condition will have a cluster value of around 43. There are two approaches you could take. You could either use the more conservative, which is the greater of the two thresholds for both, or you could use separate thresholds for each of the two. Consider the two values and how similar or different you think they are when considering your response. Question 6. What happens if we change the p-value? What strategies can we implement to prevent p-hacking? Now, let us take a look at the effect a mask has on the cluster correction. Applying a mask to the cluster correction will give you a smaller cluster size, as we are no longer accounting for the voxels that are active outside the brain. Here, we can see on the left side a cluster correction performed using a mask, and on the right side, we have a cluster correction performed without the use of a mask. The correction on the left, performed with the mask, has a cluster size of 47, while the one on the right, performed without the mask, has a cluster size of 54. Let us take a look at what would happen if we altered the p-value to 0.005 instead of 0.001. Using a greater p-value, such as 0.005, will produce a greater random arrangement of clusters, so this will increase the random cluster size. In this comparison, on the left, we have a p-value of 0.005, and on the right, we have a p-value of 0.001. We can observe that the cluster size of the p-value at 0.005 is much larger. It is 93, versus the cluster size at 0.001 is only 47. This shows us an increase in p-value will create a larger cluster size. Try playing around with different p-values and see what results you get. Let us take a look at what survived the cluster correction. Once again, we are comparing this to the NeuroSynth database. On the left, we have the NeuroSynth database, and on the right, we have the areas that survived the cluster correction. For the fusiform face area, we can see that there is still activation in the left FFA, but not the right in the cluster-corrected data. For the amygdala, we can see that both the left and right amygdala are active in the cluster-corrected data. For the STS, we can see that there is no STS activity that is preserved in the cluster-corrected data. For the OFA, we can see that both left and right OFA are preserved in the cluster-corrected data. Now, just to summarize, we will compare the Bonferroni false discovery rate and cluster correction. What we can see is that the Bonferroni is the most conservative of the three methods. The false discovery rate is the most liberal, and the cluster correction is similar to the false discovery rate but slightly less liberal. We can see that the Bonferroni is too conservative for our purposes. It may be okay for individuals, but even then, it is still quite conservative. The cluster correction works well, but it runs the risk of false positives due to the high degree of flexibility. In turn, the FDR is the most liberal of the methods, but it therefore may be more susceptible to false positives or type 1 errors. Now, we suggest that you take some time and run all three corrections and compare the results to each other. You can try the corrections at different threshold levels and using them for different conditions, such as faces minus body, faces minus scrambled, or faces minus hands.
We've just about reached the end of our tutorial. Here are a few important take-home messages. Choosing the correct correction method and criteria can be quite tricky. Mathematical modeling has shown that the probability of false positives increases with the flexibility of the method of analysis and selective reporting of results from favorable analyses. It's important to take existing literature into account when considering what corrections to use. In the case of our data, we know that based on previous studies, that in the faces condition, there should be activation in the fusiform face area, the FFA, the occipital face area, the OFA, the superior temporal sulcus, the STS, and the amygdala. So methods that preserve the activation in these areas are more suitable. It is important to note that just because a study doesn't show activation in a region which is supposed to be activated in response to a given stimulus, that the study is completely wrong. Rather, there may be other factors such as too few trials or not a large enough sample size which may be limiting the study. It is therefore important to take all of these factors into consideration when designing a study. The aim of this tutorial was not to impose any definitive idea of the ideal correction method, but rather to show you the benefits and limitations of each of the three different methods: Bonferroni, false discovery rate, and cluster correction. Furthermore, the important point to note is that in most cases, corrected data is preferred to uncorrected. Therefore, it is important to understand the unique merits that each of these methods brings to different datasets. Congratulations, you've now reached the end of the tutorial. Just as a reminder, for more detailed information on everything that was covered, please refer to the tutorial handout.